times. So I really only, by the way, centripetal acceleration, correct. That picture, incorrect. I forgot to update the picture. So let's go over the questions. I will just go to the answers on the ones that everyone got right. Everybody got a lot of things can act as a force, what cannot. This time everybody got acceleration. So our work on that last class period apparently finished off the last people who didn't get it. Number 3, for every action there is an equal and opposite reaction. What does that mean? For every action there's an equal and opposite reaction. Because knowing the words, most of us knew the words. What does it mean? That's kind of where it's important.
If you apply a force to something, it's going to apply the same force to the part.
Right. You apply force on something, the action, it's going to apply an equal force in the opposite direction on you. And then the last one that everyone got right, when a ball is dropped from a tall building, what happens assuming no air resistance? If there's no air resistance, then its acceleration is constant at g. In real life, what happens? The acceleration decreases in real life. So why do I teach you this approximation, assuming no air resistance, and then freely acknowledge that that's not the way it actually works? And no, it's not because I'm evil. Well, it does, but at the beginning level, we want to try to make it so it's easy for you to do the calculations. And it's much harder to do the calculations if you're going to include the air resistance, which is proportional to the speed. And so we leave that off. We leave that off in general physics as well. It's not until we talk about it a little in like physics with calculus class a little more. But okay. So the one where we didn't have agreement, and in fact, I think there were more people who answered this than answered correctly. So assuming constant acceleration, what shape is the position time graph for a projectile? Let's just recall, if we had position as a function of time, if we start from here and we drop it, we'll start at a position of 0. That was silly to say. Start it at a position up there at time, position 0 at time, not 0. Forgot which axis was which. Position is a function. That's what I did wrong. I flipped my axes from what we normally do. It still would have been correct shape, but I would have drawn it wrong. With constant acceleration, the speed is constantly changing. And the speed is the slope, and so the slope is going to be constantly increasing. And so you get something that looks like that, which is described as parabolic. The answer that a lot of people said was linear. Linear would be doing a straight line, but that's not what it does. Any questions about that one, because there were a lot of people who answered it incorrectly? People who answered incorrectly, okay, I don't want you to even say, yes, I understand now, because then that would be asking you to say, yeah, I did it wrong. That's not a cool thing to do. But I hope you understand. If you don't, come talk to me. We'll work things out. Okay. We ended last class period where I talked about the Mr. Ed trying to pull the cart, and Mr. Ed saying, but Newton's laws say it's impossible. Because Newton's third law says, if I pull on the cart forward, it's going to pull back on me with an equal and opposite force. So the sum of the forces is 0. Newton's second law says the acceleration is the sum of the forces divided by the mass. And what was the flaw in Mr. Ed's logic? They're acting on different things. And Newton's second law has to be applied to one object. Now, your object is something you can choose. So, with that, I didn't include that picture this time. I just went straight to another one. But in that picture, instead of that, I'm going to talk about the variant I ended class with. a tug of war between two teams. In this case, it's mano a mano, like in the All-Stars competition that I watched every year religiously as a child, always rooting for the Raider representative. You know, Dave Casper was on there, something like that. Okay, so you have these two teams pulling on the rope. You could choose your system to be this right here. If I choose that, what forces do I have in the horizontal direction? I have the rope. In what direction is the force that a rope applies? Going away. So I'm going to have the force of tension going like that. What other force horizontally is acting on that person? The force of friction, which is going to be acting this way. And so what's going to decide if that person accelerates forward or accelerates backward or stays at constant velocity? Well, it's not just the force of the other person. The force of the other person is transmitted through which of those two forces? Tension. So the force the other person pulling is transmitted to them as that force of tension. What did you say, Jennifer? Okay, friction. You have these two forces, and it depends on which one's bigger. If the force of friction is bigger than the force of tension, then you have a net force to the rear, and you pull back, and you are winning. But if the force of friction is smaller, then you're going to accelerate forward and lose. So it comes down to those forces. I could have also said, I'm going to make my object everything inside this box. What forces do I have to add when I make it that box? Okay, I'm going to have the other force of tension and the other force of friction. Now those force of tensions, because they're the same rope, and of course we're doing an ideal rope here, and it's a pretty darn good approximation with the ideal rope, those forces of tension are equal. So if I have these two equal forces pointing in opposite directions, what do they add up to? 0. And so then I'm left with force of friction 1 and force of friction 2, and what decides which team wins? The one that's getting the higher friction. Now, force of friction comes in two varieties. Static and kinetic. Static means stationary. Kinetic means moving. I'm not going to write moving is an O there, by the way. I am not going to write stationary next to static because that's a little too redundant. So you have static friction and moving friction. And you might wonder, what causes these frictions? Well, static friction is a frictional force when something's not moving. So I have, for instance, these magnets here. I push on them a little, and they don't move. That's because there's a static friction. That static friction is always going to push whatever direction is necessary to keep it from moving. So if I'm trying to push it toward you, the static friction is going to be pushing the other way to counter my force, to make it a net force of 0. And that static friction, it's whatever is needed. So we have a less than or equal sign. And then we have this thing that we call the coefficient of static friction. It's a number. How's that number determined? Experimentally. Somebody sits here and they push and push until they get to the point where it slides. And they, when it started sliding, how much force did I have? And what was the weight? Because the last part is times the force normal times how much the surface is pushing up into it. So the force of static friction is less than or equal to that maximum value. And it's caused by things like the conformity of one surface to another. Let us say that you have two surfaces that are super smooth. If they're super smooth, then those two surfaces, so here's surface 1 here's surface 2. If they're super smooth, they're going to slide over each other real easily. Whereas if they're rough, if instead of being like that, you have one surface is like this, and the other surface is like this, it's going to settle a little bit in, so you have it kind of like with my fingers spread out a little bit, and they don't slide sideways easily because they've dropped in between. I have to lift them before I can move them sideways. Now, even if you have things polished as smoothly as you can, no surface is atomically smooth, so you never have no friction. Now, with something like ice, it's pretty smooth. You get a little layer of water on it. It gives you something that will help to lift you away so that you slide a lot easier. And so ice with water on it has a very low coefficient of static friction. Now a lot of us, well, these days kids go snowboarding instead of snow skiing. But you probably still put wax on your snowboard, right? Eh? I'm looking at somebody who's wearing a Copper Mountain shirt. Oh, okay. Good man. I used to intentionally spray snow on those snowboarders who just sit in the middle of a run and block it. I have this, well, bias. As you already know, when we talk about the Raiders and the Broncos, I have biases. Okay, so you put wax on your skis to try to reduce that coefficient of friction so that your skis go more smoothly. And of course, anyone who's done much skiing knows that you actually have to match your wax to the conditions, to the temperature, to the moisture of the snow, because you can have drier snow or wetter snow. And that's to try to reduce this coefficient of friction. Now that's static friction. If something is moving, the force of kinetic friction is equal to the coefficient of kinetic friction times, again, the force normal. The equations look the same, but there are two differences. What are the two differences? They're pretty simple differences. Okay, one has a mu sub s and one has a mu sub k. Those coefficients are different. The coefficient of static friction is always greater than or equal to the coefficient of kinetic friction. That means static friction is always a little bit more, or at the worst, equal to kinetic friction. So once you get something sliding, it's going to take less force to keep it sliding than it did to start it. I actually don't want to leave that there, or it'll become magnetized and ruin a demonstration. So static friction can always be higher. The other difference, equal versus less than or equal. Static friction will be whatever friction is necessary to make it not move until you've reached the maximum, and then it slides and you no longer have static. Kinetic friction is always equal to this, and its direction is going to be opposite to the direction of the sliding. Now, with it slick out there, as you're driving and you come to an intersection and you press the brakes, your car might have anti-lock brakes. How many people's cars have anti-lock brakes? Not many. Of course, the other question would have been how many people have a car? Probably would have been the same show of hands. Okay, those anti-lock brakes, I got a car 2011. First time I had anti-lock brakes. It was really weird. The first time they kicked in, I thought I'd broken something. You guys, you know what anti-lock brakes are though, right? Nope. Okay, anti-lock brakes are brakes, a mechanism in the brakes that's designed to use this information right here to best advantage for stopping the car safely. So with the anti-lock brakes, ran out of space. I want to stay on this slide. There we go. With anti-lock brakes, I'll just put time on this axis, and we'll put the braking force here. For a normal person, if something happens and you're scared, you just jam on the brakes. And when you jam on the brakes, you basically stop the wheels from rotating, right? That's what the brakes do. And so the force of friction is quickly going to go from very low up to its maximum value for static friction, and then it will drop down to its kinetic friction. Since the coefficient of kinetic friction is always lower than the force of static friction, that means that your braking is not as high as it would have been if you weren't skidding. There's another disadvantage to skidding is you lose the ability to steer. Your steering is pretty much limited to what you would have with a rudder, rather than actually having traction to steer you. Because once you're skidded, your tire doesn't care if it's going forward and skidding or going sideways and skidding. It's going to do the same thing. So you lose steering when you're skidding. So here's what the anti-lock brakes do. The anti-lock brakes detect when your tire has stopped rotating, and it releases the brakes. But then it instantly hits them again. So when it releases the brakes, the tire starts rotating, the skidding stops, right? But as soon as that skidding stops, it hits the brakes again. So what happens is your braking does this. And so you have short periods of time when your friction is dropping and it's skidding and you don't have steering. But for most of the time, it's not skidding, you still have steering, and you have, if you look at the average of that blue, it's higher than what you have if you were just skidding with the red line. So you have higher braking force, which means you stop quicker, and you can still steer. It's really a marvelous invention, unless you're like a pro driver. Because a pro driver can brake to the maximum, they feel it start to brake free a little, and they soften up, and they just keep it right there. So if you were a pro driver, it would be possible to bring it up here and just keep it like that. And that would be your best possible scenario. So the anti-lock brakes are better for most amateur drivers, but for a pro driver they're not as good. So you would put anti-lock brakes in your Formula 1 car, your NASCAR racing car, because those guys are going to be able to do a better job of braking than they would with the anti-lock. But for you and me, we probably are better off with the anti-lock brakes. And kind of funny with it so slick. This morning I was stopped at the intersection where my house is on the ice, because you know how Lincoln takes care of roads. I let off on the brake, might have been going half a mile an hour and pressing the brake again. Anti-lock brakes don't kick in because it's like, well, you were stopped and you're still stopped, right? No, my car's going, phew. It's a lovely feeling. Okay. One last question about why the static friction is always higher than or equal to the kinetic. Because to get rid of the static, you have to do that. You have to do essentially lifting a little bit and then get it to go sideways. So it's kind of like you have to push the weight up the ramp first, and then you have it. The kinetic friction is just going sideways, but no longer lifting. So that's frictional force and how it works. Any questions about friction? Because that's all I have to say about it. Actually, I do have one more thing. That coefficient of friction depends on the surfaces. So, for instance, steel on steel, polished steel on polished steel is a very low coefficient of friction. Hence, in our car engines, very low coefficient of friction. But we still want to make it lower, so we put oil in there. The oil's job is just to keep the steel from touching the steel, and that lowers the friction quite a bit more. If you have rough surfaces like untreated wood on your hand, just rough cut wood, well, that's a really high coefficient of friction. And of course, you get a lot of wood sticking in your hand as a byproduct there. So it depends on the surfaces. Car racers rely on friction. Right? The more friction they have, the faster they can start, the quicker they can brake. And so they do everything they can to increase the friction in those tires. And of course, they play with a lot of things, air pressure and temperature of the tires. If you've ever seen car racers and wonder why before the green flag drops, they're weaving back and forth. When I was 6, I thought it was because they had really bad control of their vehicles. Or like my dad's car, it had this much play in the steering wheel, so you kind of got to go like this. No. It's because they're making their tires slide a little bit and warm up. Because if you rub your hands together, they get warm. Same thing happens with the rubber. And when those tires get warm, the rubber gets tackier and they have better friction. And so like the first lap or two after a start, it's a little more dangerous because they don't have as much friction with their tires because their tires aren't as hot. But if the tires get too hot, then the rubber gets too soft and it comes off the tires. It's a very tricky game they play. All try to take advantage of this physics. Okay, another question. Trust me, centripetal acceleration is my topic du jour. It's just I had like 3 slides before there, and we've gotten only... Actually, we didn't talk about the last one. The last one, go back. What makes the car move? I've drawn, assuming no air resistance, I've drawn all the horizontal forces that the textbook has on the car. What makes the car move? It's the force of friction. If you look at the forces that are shown, the car's tire is pushing the road backward. And according to Newton's third law, if the car tire is pushing the road backward, what does the road have to do? Push the car forward. And that's the force that is actually making the car move. Because the force of the car pushing the road backward, what's that acting on? It's acting on the earth. And so it is, you accelerate forward, you're making the earth's rotation change a little bit, right? Really, really tiny amounts. So minuscule that we would never consider it realistically. But you are, because you're pushing the earth that way. And then the force of friction is acting on the car. So that's the only one of those two forces acting on the car. That's what makes it move. Okay, now we can go to the next picture. Here we have some toys. Went down my basement last night, found toys everywhere. Apparently the grandson had been there. So you're pulling on that. If those two carts have the same mass, and you're pulling, they're of course, you're going to accelerate, right? Because you're pulling. Assuming there's no friction, your net force is forward. How would the accelerations of those two cars compare if I'm pulling?
First one will accelerate first and grab the second one.
Okay, Andrew has a good technical answer. I studied shock physics for a while, and in shock physics you're studying the shock waves going through an object, and you have to get down to that level. When a ball hits the floor, the top of the ball is still moving down because it doesn't know the bottom's hit the floor yet. And that's basically the level that he's talking about. When you pull it initially, the front one moves, but then when the back of the front one starts to move, it pulls the second one. So once we've got past that, once it's been transmitted to the second one, how's the acceleration of the first one compared to the acceleration of the second one? They're the same, because they're going to have the same velocity change over the same time. So if they're accelerating the same, if the two cars have the same mass as well, so it's a given in the slide, they have the same mass. They have the same mass and they accelerate the same amount. What does that tell you about the net force for each cart? The same. So the net force on each cart has to be the same. But let's look at each cart as a separate entity. So if I look at the first cart here, what forces are acting on M1? Horizontally only. Let's ignore friction. We got, because it has wheels, we have what we call rolling friction, which is really, really small. For your automobile tires, we actually intentionally have them so that they collapse a little bit, right? They're not super inflated. And that's so that they will grip the road. But by making them a little not underinflated from what they could be, so they grip the road, you're actually increasing the rolling friction. It takes more energy. If you overinflate your tires, it takes less energy. Why don't we do that? Yeah, it's not safe because we kind of want to stay on the road and not slide off. So you could increase your fuel economy while making your driving riskier. We don't recommend that. Okay, so back to this. The rolling friction is really small, so like the air resistance, we'll ignore it. What other forces? Okay, there is a force. I'm going to draw it down here. There's a force of cart 2 pulling back on cart 1. And so if I take the net forces there, the net force is equal to the force pulling minus the force of cart 2 on cart 1. Now let's look at the second. What forces are acting on the second cart? Horizontally only. The force of cart 1 pulling on cart 2. Notice one was F12, one was F21. Those are Newton's third law pair. Force of one acting on the other is equal to the force of the other acting on it, but in opposite directions. So we know that force 1,2 has to be the same magnitude as force 2,1. And so if we look at this, I forgot to put some of the forces on 1 here. So we have those two equations for the sum of the forces. But if they have the same acceleration, then we have this is equal to m1a, this is equal to m2a, and, my blue a disappeared. I may have forgotten to write it. If the accelerations are the same and m1 is equal to m2, then I'm going to have F12 equals m2a equals m1a equals the force pulling minus force 2,1. But the magnitudes of force 1,2 and force 2,1 are the same. They're equal and opposite. The opposite I already took care of by putting the signs in front opposite. One was a positive sign, one was a negative. So the magnitude is the same. So F12 is equal to the F21. So if I add F21 to both sides, and so I have the force between them is equal to the force pulling divided by 2. Now, if you think about that answer, it actually comes back and it's really kind of obvious. When I pull on the first cart, my force has to accelerate both of the carts. So that force is supplying the acceleration for both of them. Since they have the same mass, that means it had to be an equal force to accelerate the first one and to accelerate the second one. So the total force had to be twice the force necessary to accelerate a single cart. And so the F12 is the force necessary to accelerate a single cart. The total force had to be twice that. But it's kind of interesting to go through the work because oftentimes you just blindly think, well, the force between them must be equal to the force I applied in the first. That's not correct. And if the masses weren't equal, then the force between wouldn't be 1/2. It would be proportional to the masses, which we're not going to do that calculation right now. We could have done that calculation. We would have had the same A's, but M1 and M2 wouldn't equal each other, so I would have to solve one for A and then put that in the other. Okay, now a clicker question. Two blocks with the same mass are connected by a string and are pulled across a frictionless surface by a constant force. Frictionless surface, the same as having the wheels where we assume no friction there. Will the two blocks move with constant velocity? There we go. Okay, so our answers were 5 and 4. Even though I've gone pretty slow and haven't started the topic du jour, we only have one more clicker question, then we're going to start talking about rotational motion. I want you to discuss this with your classmates. It's pretty close to a 50-50 split, and so I want you to discuss with your classmates and try to combine your thoughts and see if we can move toward a more correct answer instead of a more incorrect answer.
Every time we
Discuss why it's going to be your answer. Why do we get it? Seemed like the right That's the three you have this.
Again?
Acceleration.
Well, based on the numbers, I can assume you had it correct there. Since we guys all have your discussions down? Let us answer again now. We had one person change their vote. Well, who changed their mind? Kayla. Good job. Who convinced you to change your mind?
We kind of all had the same answer, I think, and just the past 2 times I've always kept my answer and moved on.
I was looking for somebody who gave you the insight. Okay, when you're pulling, if the net force is not 0, what does that tell you? That the acceleration is not 0. Both Newton's first or second law would have told you that. And so since there's no friction to oppose this, you're pulling the cart, the net force is not 0, or the block, excuse me, the block. Net force is not 0, hence they must be accelerating. So they cannot have a constant velocity. So you could have stopped your reasoning right there. But I did have answer 4 wasn't just they don't have constant velocity. He said they have constant acceleration. If the net force is constant and the mass is constant, then acceleration being net force divided by mass is also going to be constant. And so the correct answer was the acceleration is going to be constant, the velocity is going to be increasing. They're held together, so they're going to have the same, each cart will have, or each box has the same acceleration. At any given moment, both boxes have the same velocity, but the velocity is going to be changing. Okay, I think there's one more clicker. Yep. Will the tension in the connecting string be greater than, less than, or equal to the force F? For you, Daisy. Okay. Colby, you're a bad influence. You had it right. You said, oh, wait, and the two of you changed your answers. Right? Wasn't that you that said, oh, wait? No. That was you? Well, these are what people answered. What did we just do with the 2 carts with the toys in them that had equal mass? We determined the force between them, and what was the force between them compared to the force pulling? Here's what we found.
But wouldn't you add the tension both ways?
Well, you have the force of 1 on 2 the force of 2 on 1, those are opposite directions, but they still have the same force. They're both equal to the tension on the string. And so that tension is, if the masses are equal, 1/2 of the force you're pulling. If the masses are not equal, let's say the second mass, the one that's trailing, is a higher mass, then it's going to be bigger than 1/2 but less than the full pulling force. Like I said, it comes down to ratio of masses. So that force in between doesn't have to be as strong. Hence, you can see the fun little demonstrations where you have, well, a string that has, 2 heavy masses on it, and you yank the string up, and it always breaks, above the top one, not between the two, because of the tension between the two being smaller than the one that's pulling. All right, now we're going to really go to rotational motion. So we've got the little, teaser question. Is there a relationship between how the Earth rotates around the sun and the moon rotates around the Earth and how a car goes around a corner? We don't ask these teaser questions unless the answer is yes. Yes, there is a relationship. So we're going to talk about what is going on, for instance, when a car goes around a corner. So let us suppose that I had a vehicle that hadn't slid off the road that was coming around this corner. So I have a car, and its velocity is like this. If it's going to go around the corner at constant speed, is its velocity constant or changing? Changing. Why is the velocity changing if it's going around the corner at constant speed? Because it's changing direction. Okay, we got that. And so there's a force required to cause an acceleration. A changing velocity means an acceleration. And so there is a force that is necessary to make it change direction. And we actually showed earlier that that force is always perpendicular to the velocity if it's just changing the direction. Right? When we talked about the car having 3 accelerators, the steering wheel caused an acceleration that was perpendicular to the velocity. So that's what we're going to study here in 10 minutes. So, clicker question. I have a string going around my head, and at some point A, and let's say A is when the ball is right here, it asks what direction is the velocity, or bob, what direction is the velocity of that bob? And so your answer's there. Only 1, 2, and 3 because 4 is a curved line and we're looking for directions. Okay. We all answered and we had 1, 2, 6. Well, we had a majority. And the majority was correct. When it was out here and going around in a circle, its velocity was going like this. So it was going, at this point, straight toward the back of the classroom. And as it went around my head, the direction of that velocity was constantly changing. Because that direction is constantly changing, you know there's a force necessary. And what direction does that force have to be? Perpendicular, which conveniently enough is the direction in which the string is leaving the bob, right? So there's a force of tension that's pulling it toward the center, and that's what's making it go in a circle. Now the next question says, the string snaps at this instant. And so if the string snaps at this instant, which path, now this is only looking down from above, so we have no vertical motion we're concerned about. Only motion that you see, in one plane. So if it's like this, we wouldn't be talking about it going up or down. Just what direction does it go in the horizontal plane. If the string snaps when it's right there at point A. I have not moved forward, it turns out. So you have to answer starting now. My bad. So, Andrew and Daisy are still not in. I have to let you know because you probably already answered before I changed. All right, so everybody's answered. We have 0, 2, 6, 1. Now, this is a science class. We just talked about this yesterday in a division meeting. One of the things that we want all of our classes at this level to emphasize is the scientific method. So, taking this a little bit backward, if we were doing this with the scientific method, what would the first part of the scientific method require you to do? Observe something interesting. So we're going to say we observe that when I swing this around a circle, if I let go at some time, it will fly off. Right? I did that. When I was a little kid growing up in Liberia, we had slingshots, and I loved to play with them. And of course, when you use a slingshot, you don't just let go, right? You also do a little throw action. In fact, some people, and the way we learned to do it out there is, you go like 3 times around, then you do it. Some people just do a motion like that for it. Anyway, so we observe something. What's the next step in the scientific method? Create a hypothesis that does what 3 things? What?
Predict.
Okay. It needs to make predictions that can be tested. That's one of the 3 things. 2 more. Remember, these are going to be on the first exam, along with your application thereof.
It's based on scientific ideas.
It needs to be based on scientific ideas.
And it needs to be testable.
That was actually, that makes predictions that are testable. There's one more thing. Based on scientific ideas, it makes predictions that can be testable, and the most obvious of the 3 needs to explain why it happened. So we would take this and say, okay, why did it happen? Why do you think that it went flying off? Since Tyler answered most of my questions, I'm going to ask somebody else. Colby, why do you think it went flying off? Okay, well we need something more than that. I let go. I mean, it could have just hovered. Why did it go flying off?
Because the forces acting.
Okay, because the forces acting on. While I was holding it, what forces were acting on? Tension. And there was gravity, but we're not looking at the effect of gravity here. Just the horizontal plane gravity was vertical. So we had tension. And when I let go, there was no longer the tension. So what does that tell you? The horizontal forces were 0. And so if the horizontal forces are 0, what does that tell you about the acceleration? Should be constant at 0. And so if there's 0 acceleration, what shape should the path have? Straight line. So our hypothesis would be something like, okay, it went off in a straight line because the net force was 0. And then, we could be a little more tricky and say, what direction should it have gone? If the acceleration stops, what does that tell you about the direction? If I'm traveling and there's no acceleration, what's happening to my direction? Staying constant. So it should have gone in a straight line from the direction it was going the instant the force stopped. So what direction was it going the instant the force stopped? 1, 2, 3, or 4? Well, 4 is not a direction. 1, 2, or 3? 3. So that means our hypothesis predicts that it should follow path 3. But of course, we need to test that. I didn't pay attention to where I let go of it before. Well, I kind of did because I didn't want to throw it out here and hit somebody. But now let's try it. Let me try to let go at the instant when it's right out here. Now it's kind of hard to be perfect on this, but I will try to let go at the instant when it's right there. So don't let it hit you. Right? It certainly did not go the 1 direction. Also didn't go the 2 direction. It went the 3 direction. So there we did an experiment, and the experiment could have disproven it, but it confirmed it. So now that we've confirmed it, where are we in the scientific method? Yeah, we got to go and check a different way. We're not like, woohoo, we got it right, we're done. That's not how scientific method goes. You have to test again and again and again. So the correct answer was the one that 6 people answered. It's going to follow path 3. Why do we spend so much time in this class on the scientific method? Why is it a point of emphasis for all of our 100 level science classes? It's used throughout all of science as the way we understand anything and have faith in anything. If you don't understand the scientific method, you have really no reason to have faith in scientific conclusions because you don't understand how they came to them. They might have come to them, like Colby says on every question, through magic. Don't ever answer that. There are 2 questions that Colby put in that had magic as the answer, and neither of those are the correct answer. But I left them there, so you just have that little extra hint. I think it's Colby. I'd be really embarrassed if it wasn't. Okay, so we've gone through this whole process of thinking how it works. So, in the end, using some either complicated math or some not as complicated calculus, we can determine that the acceleration of this ball when it's going around in a circle has to be equal to the speed squared divided by the radius. So if I bring it in tighter and I go the same speed, because it has a smaller radius, what does that tell you about the force necessary? You're dividing by radius. So if you divide by a smaller number, what does the force become? It becomes bigger. So the smaller the radius, the bigger the force has to be. The bigger the radius, the smaller it has to be for the same speed. What about if I speed it up? I'm going to actually stick my finger in here so I don't have an accident. Maybe, okay, that was a bad time. I won't. Okay, we'll just say, okay, what if I speed up? So I start slow, I make it go faster. What happens to the acceleration when it goes faster? It goes up. It's proportional to speed squared. So if I double the speed, it's 4 times the acceleration. Well, using Newton's second law, that means the force to make it change direction has to be 4 times bigger. That's why speeds have to be slower going around turns, because you have to have a force to make it go in the turn, and the faster you are, the bigger the force is. It's not just proportional to speed, it's proportional to speed squared. So if they consider it safe to go around a corner when it's at 30 miles an hour, and you go around 60 miles an hour, you're going to have 4 times the force pushing you in to navigate that turn. So that's what the centripetal acceleration is. Centripetal is a word that means toward the center. And we will talk about the difference in centripetal and the fictitious centrifugal on Monday. Have a sweet weekend. Good luck to the Broncos, even though I don't want them to have good luck, because I'm just a hater.